Okay. Can you hear me? I know. Uh, is it better this time? Is it? Can you hear me? Is it? Can you hear me at the top? Good. Um. So first thing is probably you might have noticed is I put up the homework uh on the blackboard. It's starting officially starting today because you usually have 2 weeks to finish the assignment, and don't notice that it's a combination of topic 1 and topic 2. We will basically you can do except the question 6, which we'll cover today. It shouldn't be difficult. I mean, if you know what we have been doing, it shouldn't take more than an hour to finish the whole assignment from beginning to end. Of course, if you are not acquainted with the knowledge, then probably you may take some time to read the thing, but you probably notice there will be some variation of the example we cover in the class. So as long as you have listen to the class, or you can look at the record lecture, and then you will be able to find the answers. Okay, so just when you submit, just try to use the template so that the TA think this template would make his grading easier. So try to follow that. Just submit in the blackboard. Just you can either do it by hand or do it in computer, whatever you like. You take computer, you can just take a picture. If you do it by hand, it's up to you what method you use. And that's it. If there's no and unfortunately, last Friday, the lecture, I think some technical issue, I cannot do that. You can go back to the session F, they will have the same stuff there. So luckily, we have a parallel section. So even though there's some issue with the Zoom, I was still able to take care of that. But I have my record on, so shouldn't be an issue, hopefully. I mean, who knows what happened. So now we are going to, what we're going to do today is to finish this chapter probability. In particular, we will go a very detail on the Bayes theorem, which essentially one of the most important part of the course, right? Because Bayes theorem is indeed something probably new to many of you, and actually it's very useful when we try to apply business decision, right? Because basically is we learn some new information, how it changed the way we view the world or how we predict the future. That is the Bayes theorem tell us, right? And very quickly, we will go over what we have covered in the probability, okay? And then we go back to the Bayes rule, because over the weekend probably it's not easy to remember all the details, okay? But probability start from the idea what we call relative frequency, right? It's you do an experiment, the random experiment many times, and the ratio of the outcome that favorable to the event to total number of experiment will be the probability of the event, right? And this definition comes from data, right? Suppose the data, you get that, and then you, from the historical history, you know how the ratio, this thing happened, then you have a quantitative judgment, right? If you think history repeat itself, then that is how you quantify this event is more likely than others, right? Because ideal probability is try to understand the idea how likely this event will happen, right? You compare two events, right? Then you try to say, okay, you say A is more likely than B, how so, right? And this is the way you would do it, and you would able to say how much more right? How much less is by the number, right? And because of the fraction, it must be between 0 to 1, okay? And this probability is based on the idea either is coming from data, right? Or you have some hypothetical experiment, right, in your head, right? But basically the idea is coming from data, right? And the idea is that if we want to extend it to abstract setting, or you want to extend to some derive the probability based on model, right? Either the physical model or some mathematical model or any finance model or the accounting model, right? I mean, banks, right? When they approve credit cards, right? Or credit to people, right? They have to estimate how likely you're going to default, right? And then how they can do that is a model, right? The model, how it comes with some assumption, right? Then relying on this may not be good enough, right? So you need to come up with probability that we don't have data on, right? To extend that. And how can we do that is by looking at theoretical probability, and you need to understand what assumption behind for probability to work, right? So that's why we start talking about operation on set, right? We talk about and or not, right? And this is the building block for our abstract probability, right? And intersection, to remind you, is and, union is or, complement is just not, okay? And just to remind again, intersection is common element, okay? Union is all outcomes, right? And not is not there, okay? So don't worry, you have that in your assignment, you'll work out them again, okay? I hope that would be, I think the assignment, I think the assignment, did I ask the question in the assignment? Yeah, I kind of asking the assignment, but not exactly that simple, but yeah, I do. You would understand and or not, those kind of idea. And based on and or not, or based on union, complement, or intercept, we can define 3 important events that will be useful for our construction of abstract probability, right? First one is what we call the mutually exclusive, means that they can't happen at the same time. If one is true, the other is not, right? Remember our original example, if you are being in New York, it can't be London, right? Say, right? So that is the idea. And the exhaustive event means at least one of them is true. It can't be both of them are false, okay? So that's the idea. And partition means one and only one of them will be true, okay? So that is the idea, okay? So there are 3 ideas of the event. So what remains, what we have to do is to formally define what is abstract probability. And looking through axioms, we know what is the underlying structure for probability, because they are only thing we need, 3 assumptions, the only thing we need when we say probability, right? Because probability in this case is no longer a number, rather it's a function, which it means you give me an event, I give you a number, okay? It's a function. It's not simply a number. It's a probability of an event. It's not probability is 3. It's probability of event A is 0.3, so on and so forth. And the number that function give is from axiom 1, it said is always from 0 to 1, right? And this axiom 2, it just said the probability sample space 1, okay? So do note that it does have some meaning for this one. It means that we know all possible outcome that is coming from the case. And I have iterated to understand it's just like if I toss a coin, right? It's likely to be head or tail, right? It can't be like the movie, the coin disappears in the thin air, or a rabbit comes out, right? Or you go to another universe. No, right? So it must be, you know what's going on, okay? And that would be the case. And the very last one, right, that is the one that has most bite, is what we call the addition property, which essentially said if you have union of mutually exclusive events, right? A is a union of event there. It just simply the probability of that union will be just probability of the sum of each event. Okay, it's just basically saying that you can do divide and conquer. If you have a big event, you cut in small parts. As long as they are mutually exclusive, you can calculate each part by part and add them up, then you're done. Okay, and that's the idea, right? So the idea is the probability events of even number will be exactly equal to the sum of probability 2 plus probability 4 probability 6. Not more, not less, exactly the same. So that is the very important assumption. Without that, nothing will work. And probably you will say, okay, this is trivial, right? And yeah, it's trivial, but the real bite is taking this cut into infinite, right? But we are not talking about math in the class, but if you try to look at the paradox of infinity, go to YouTube, there are many, and you notice when you talk about infinity, your mind explodes, okay? And we really, I mean, usually we are unable to understand. I mean, actually, it takes human to understand infinity, taking them for more than 2,000 years. I mean, since the Greek people, they understand infinity is a lot of paradox, right? And even way until maybe recent 100 years, people have understand of infinity more, right? But still, I don't think the current knowledge, we still don't fully understand infinity. But at least we know that this also holds for infinity. And you may ask, what is significance of infinity? It's because when we talk about probability, or we often times talk about infinite event, even number of outcome, because of, say, stock market, right? The stock price, the number you can see is usually you use a number to do it, is a many number is possible, right? There's no limit of what number is possible, right? Because 1 is possible, 2 is possible, 1.5 is possible. Any number you give me 2 numbers, anything in the middle is possible, right? So, I mean, infinite possibility. So you have to make the probability work also for infinite. But anyway, it's technical, so you don't have to worry about this. But just to bear in mind, this work for our when the number of outcome is continuous, right? And we do need that. When I talk about random variable in probably the end of today's class, we talk about something about that. But you will see how they're connected. And numbers are actually mutually exclusive, right? So that's infinite, right? Because the stock index today is, say, 20,000, right? And 2001 are mutually exclusive, right? If you equal to that number, cannot be equal to the other number, right? So that's why infinite is needed. But anyway, don't worry about that. It's not our concern, but just let you know, the mathematics behind is rather deep, but we sidetrack on that. We keep that aside and assume mathematicians do things for us. Okay, just like when you have the iPad or your laptop, right? We don't need to know why it works, right? It's a job of engineer, right? And then we just need to know, when it works, then done. Okay. So here is just some rules that derive from the 3 axioms. The first is complement rule. It essentially said A and A complement add together must be 1, because that is coming from axiom 3, right? And 2, right? And I'm not going to do a proof, but the idea of this is saying that it simplifies calculation, right? If you want to do calculation, particular event, it's very difficult, but you can calculate the thing outside, then it's much easier, right? The simple idea is, say, suppose, go back to the question in the primary school, right? And suppose you want to know, say, you go to a farm, you want to know after typhoon, right? Some of the animals run out of the farm, right? The fence is being broken by the storm, right? And then the question is, okay, you want to count how many sheep, how many horse, how many other animals in the farm, but it can be a lot of job, right? The easiest thing is to do maybe you just look at how many animals before the storm struck in, and look at the CCTV, right? Look at how many animal has left the farm, right? And then do the subtraction and you're done, right? So it's difficult to go over the farm, especially the farm is big. If the farm is small, just go there. So same idea here, right? If the probability you want to calculate is very simple, then you're done. But it's very difficult, then probably you need to calculate outside, right? Just like here, right? Count how many A there may be difficult, but you can count things outside. So here, another thing is the rule that what happened when you want to calculate union, but they're related, right? So the rule is this addition rule. Simply means that A union B is A, probably A plus probably B minus probably A intersect B, right? And the idea is just basically remember this diagram, right? If you want to calculate the total area, which is a union, you can easily take the area of red circle plus the area of the blue circle minus the overlapping pink area, right? That's what you learn in the kindergarten. Exactly the same logic here. And here we have the with that, right? So this is the total probability rule. It's saying that probably A can be decomposed in two parts: A with B and A without B. Okay, we'll use this again very soon when the base rule in talk about the denominator, right? We'll see that, right? This one we will that, right? That's very simple graphically, right? The red circle will be the red circle without B, which is the little bit red area, and the area with B, right, will be the pink area. So it just decomposes in two parts, right? There's nothing very deep goes on here. And I think we mentioned that odd ratio is simply another way to express probability, right? Probability is very convenient, it's 0 to 1, right? But before that, people actually talk about odd ratio sometimes because calculator is not that convenient compared to ratio. Sometimes easier, and that actually still used in betting, right? Because betting is very convenient because the odd that being used in the casino or horse racing or other places talking about odds, right? If you bet $1, right? If you win $1, you lose $1. This is 4 to 1 odd, right? And if we say the odd is fair, if actually the inverse odd ratio is exactly the odd, right? So that's why odd ratio and odd, I mean, it's related in the real world, right? The odd in the real world is actually the inverse of the odd ratio, or the odd ratio against it. So, right? So whatever you like, but that is that. And we have, okay, here is important. What is condition probability? Just by definition, right? Is A and B and over B. So it's a fraction, and the numerator is very natural, right? Because what it means is, what is A if we know B is true, right? If B is true, then only thing it matters is A intercept B, because A, let's see if I can write. Because the fact that A, right, can be written as A intercept B and A intercept B complement, right? Because that is the total probability rule. And we now telling you that B is going to be true. That means B complement must be false. Okay? So that's why we only left for the first term. And probably ask, okay, now I understand the numerator, but what about denominator? Why we divide it by probably B? The reason is axiom 2. It said we must have the sample space, probably sample space equal to 1, right? So suppose A is exactly B, right? We need this guy to be 1, right? Given your B happen, probably B must be 1, right? So B intercept B is just B, right? So you need this to be 1. So we just rescale it so that it must be equal to 1. Okay? Because that's the idea. Okay. Okay, is that clear why this is true? Of course, you can do the proof, but if you don't want to do the proof, I think this one is a good example, right? Because it tells you in the third bullet point, right, the sample space strength, right? Given the L, the sample space strength. So that's exactly to show you why this is true. Okay, you can convert this to a proof, but that is not our intention. But you can easily change this to a make everything generalized. There's a proof for this statement. Okay, but we're not going to do any proof on that. But the proof will be actually the same of this one. Just make things general. So I hope you accept this. Okay, if you don't, then just remember this doesn't really matter. I think I only understand what's going on this up until I go to graduate school. So since I don't understand when I was undergrad, so it's okay you don't understand. I mean, just remember that. I mean, I guess I only truly understand once I graduate from my PhD. I get my PhD, I fully understand what's going on. Sometimes it's not easy to understand what exactly it means. You think you understand, but sometimes you don't, right? And that's what happened, right? That's what will happen, right? And you ask a man and woman divorce, why? I mean, I truly understand he or she after X number of years, right? That's normal. I mean, same idea here, right? I understand them until many years. No, I understand what's going on. So it's okay. When you learn probability and statistics for this class, sometimes you don't understand. That's normal. I mean, you think you understand, you have some doubts on here and there, but it's normal because we're not learning any proof. So in case you still worry, it's okay. I mean, this is something well established. Just take some faith and you'll work out. Okay. And the next is the multiplication rule. It essentially basically just swapping, right? If you remember the formula there, it's just swapping. Okay. You just move the denominator to the other side, right? You multiply both sides by the denominator, you get the answer. Okay. So that is nothing new, but just another way to write it. And probably you ask, okay, what's the point of doing this? Because, you know, in the world, right, we don't talk about a static future, it's a dynamic future, right? We talk about you do one thing and after that you do the other, right? Just like if many of you are the ACY, right, do accounting, right? You know, and do a B.B.A or whatever, right? You do year by year after year, right? Talking about a long time in the future, right? You do things, it's not you do once and for all, right? You do finance investment, it's year after year. You do accounting, you do audit, one object after the other, right? And that's why you do things, and which one you use depend on which one appears first usually, right? Just like this example, right? And you still recall, you just like try to draw two balls there, right? What's the probability, right? Of course, you can actually list out all the possibility, right? And actually 4 of them, right? Actually more than 4, but it's a lot, right? Because depend on how you count the events, but at least it is complicated if you actually try to do it. But this way, it's going to simplify, right? You're going to draw black ball in the first round and calculate the probability of black, second black after the first black. So that would be much simpler to calculate. And that is the goal, because we want to make our calculation easier, and this helps us. Okay. And for those of QFN, then this is actually this is called conditioning method. Okay, you conditional on B1 and 2 calculation. Okay. And yes, so this is the tree diagram that try actually incorporate all the idea that we have discovered. I mean, basically, if you able to understand this, is almost every single concept in this class will be done, right? So you can see this. You have 3 whites, right? Once you draw black, then what left is 2 black. Similar idea here. If you try to draw a white one, then it's 2 white left. Okay. And after that, this is conditional probability, because conditional on the first is black, then you have 2/3, 2/5, you draw black, right? Because only 2 out of 3, so on and so forth. So maybe I should use green color, right? So these are all conditional probability, right? And you can see the how you do the rest, right? That is the multiplication rule, right? This is how you multiply along the branches, okay, to get this outcome, right? So basically, this graph tells you how you can calculate conditional probability, right? How you are going to do the multiplication rule, right? And later you learn the addition rule, right? For example, you want to calculate the probability of having a black and a white, right? Then you'll be adding up these two, right? Because these two event is that outcome is actually count as you draw 2 balls. One of them is black, one of them is white, right? Just add them up, because these two are mutually exclusive. We just add them, right? So if you understand what's going on, actually this graph will tell you everything. But anyway, so let me. So here is the last rule, I guess last rule, right? Probably last rule. If we learn is we just combine the 2 rules, right? Here you just apply the conditional multiplication rule to the addition total probability rule. Okay. So that is the idea behind. So this is asking probability of white ball. Okay. But this one is right? Because look at the graph again. The same question asking probability of white, right? So the question is a little bit different. Maybe I should go back, right? So this is not earned, but there are 2 bets, right? Bet A and bet B, right? Bet A have 4 whites and 1 green, and B is 1 white and 1 green. You're going to do the following. One, you draw the bet, close your eye and draw 1 bet, and close your eye and draw a ball from the bet, right? So this would be first you have half of A and B, and once you do that, you're going to draw a ball, black or white. And as you can see, right, the probability of getting a white ball is coming from the first and the third branches, right? Because there's a only case you have the white, right? The other case you have green. Okay. So here then what you do is just addition rule, right? Because these 2 branches by definition is mutually exclusive, right? So that's why you just add them up, then you're done. Is that clear? Or of course you can write the if you don't want to do this, of course you're very mathy, right? Then you can just simply directly do the calculation, right? White is white, and whites come from A and white come from B, because they are mutually exclusive and exhaustive, this partition. So you can do that, right? Because B's complement is A complement is B. And then you can do the conditional doing the multiplication rule, right? And then everything is very clear there. Then that should not be a big issue for you. And next is independence. I think this is the very last one before the base rule. So independence is very simple, right? If telling B has no impact on A, or telling A happen has no impact on B, then it's independent, right? And turn out to be you don't need 3 of them are the equivalent, right? As long as you need 1, then the other will be fine. Okay? You don't need to show 3 of them. If any one is true, then it's fine. Okay? If one true, the other will be true. Okay, so there's no need to worry about, you have to check 3 of them. Any of them is true. Okay, and we actually looks very simple. Actually, we will be assuming this when we collect data for our whole course. Okay, we assume the data you collect from subject number 1, option number 1, will be independent. Subject number 2. Okay, that is random sampling. Like later we'll learn in the topic 3 or 4. That will be assuming here. Okay, so then it simplifies our case a lot. If it's not the case, that will be very difficult. Okay, some of you, some QFN will jump up and say, okay, what happened to the stock market data? Right? Stock market data tend to be related, it's not independent, right? If today's stock market, I suspect it go down because yesterday it has been going down. Maybe I can check in the break, we can see whether it's go up or go down, but I guess it's down because if it's down, it's likely to be down. So they're not independent. And when you collect the data from the stock market, the stock price, you collect the day by day, right? And this data, or hour by hour, whatever, is related. Okay, it's not independent. So to analyze those data actually require much difficult technique beyond we learn in this class. Okay, probably next class, maybe 2021 or even more. But anyway, in our class, we assume this is the data we use is more or less independent. Okay, and okay, that would be things we assume for our whole class. But I hope that will be okay. So now we're good. We go to very last rule, base theorem. So we go a little bit slow because we just review what we have done, but this will be slower. The base rule. So the base rule says the following: probably A given B, okay, is going to a fraction, B the bottom. The numerator is just A and B, right? If you just write down carefully, right? So this guy is just probability A and B, right? And this is the multiplication rule. Probably you ask, okay, what are we doing here, right? We just put the multiplication rule to the numerator, and what do we learn about that? Okay, so as we said at the beginning, what is this rule is learning. Okay, what we learn is originally our prior knowledge is A. Okay, and we learn new information, which is B. Okay, now we have another judgment is A given B. Okay, let me look at here is we come from, where are we? Okay, what we're doing is we come from the A, okay, and we want to go from A, okay, to probably A given B because we have new information from B. Okay, and how do we update? We rely on how do we know given A how likely B arise and how B arise, right? To reverse infer, right? So basically is we have some idea here, we just kind of flipping it, right? So in order to from here to here, we need to have this as an intermediate step, okay? And later you will see how we do that, right? Because in the example, we should have time to cover. We'll cover, right? A will be something like how likely you get a disease, right? And B is a medical test, right? And you want to say, given the test is positive, how likely you get a disease, right? Or you get the results negative, how likely you are not getting disease or you get disease, right? This is something we will care, right? And probably you ask, okay, how you get this, right? What is this guy, right? This guy is, right? Given how we know the technology, right? A is what? A is how like is you get the disease or not disease, right? And given you have or you don't have the disease, how likely you get the positive result, right? This comes from technology, right? Come from technology, okay? And technology or the knowledge about how things work is the knowledge we have, right? The knowledge about the technology boundary. And this guy looks crazy, right? But we actually we keep using the same method. Is this? This guy looks a bit not very friendly. Okay, how we do is we apply the rule we learned that combine the total probability rule and the multiplication rule, right? So this is a rule actually we just said, right? B given A times A, which actually is the numerator, right? And the other part will be, actually you have that in your slide a few slides ago, right? This guy, right? So we just the part with A and the part without A, right? But if you can't fully remember this, it's just this. A plus the part without A, right? So that's simply right? This first guy is this guy, right? The second guy is the second guy, right? So this is how likely you get the disease, right? And the complement this guy, so you know how to answer, right? And this is you get the disease technology. And this is if you don't get the disease, you can still get positive results. So also from technology, okay? So everything is like you have a prior understanding and update along with the technology, and that's how you update, right? That's why every doctor, okay, if you go to a medical school, they will study this. I mean, that's the main thing they will study because they do all the time. They do medical tests, right? So that's why not this year, but I think previous few years, there's some medical students in the back. They sit until this class and they go away. They just basically learn this and go. But that is the main thing. They sit in, but I guess now we're full house because I used to teach in lecture theater in the ELB, the big one. They just hire the back, but I don't think they can hire anywhere now. So, but so that's the idea. Okay. So that's the idea. Okay, we will go to example, then you will see what's going on. But do remember what we're doing for this formula is we learn information B, okay? And based on the information B, how we change our judgment on A, okay? Because that is so fundamental, okay? So I hope you get it. But don't worry, we'll go to the example slowly, step by step again. So to put in perspective, okay, that is the idea, right? Because what we want is the following, right? Let's go back to the tree. We want is probability A given B, okay? And this is the nature or judgment decide whether how A is possible, right? This is our prior, right? And we know from our technology, right? Or our knowledge tells us if you have disease, how likely you get positive result or not, right? This is from our technology or what we know, our knowledge. Technology or knowledge, right? And at the end, we get all this kind of outcome, right? And because we now know B has happened, the sample space actually shrunk to the red thing, right? Only red is relevant because we know B had happened, right? And now given B had happened, how likely A actually had happened, right? So basically just the first branch over the sum of the two branches, right? Because the sample space actually shrink to the red one, right? Because not red is not relevant, right? So that's why I write is the first branch over the sum of the first and the third. Is that clear? Don't worry, we will do it again, because that is so important. I can't afford to lose you here, because if you are lose here, then you lose the most important part from this course, right? Which is learning the base rule. Okay, besides you do the regression or ANOVA, that is a very important thing here. Okay, and what we have is this question. This question it has we go again. We'll go through this and then we'll break. Okay, and then we go to the medical example. But this is the classical one, right? And we have a and B, right? Again, the same question, right? A has 4 whites and 1 green, and B has 1 white and 1 green. The question is, now you have drawn a white ball, okay, from this process, right? The process is close your eye, choose a bat, and once choose the bat and draw a ball there. And the question is, okay, after this, if you have a white ball, which bat it comes from, right? And some of you may think is, okay, since you close your eye, then you must be equally likely that it's good. But you would think other way is like A is might likely from A, because A is more likely to come from white, right? Have more white than green, right? So to quantify this, let's do the calculation, right? So let's see what the thing, how you usually approach this kind of question. Usually just write down, I think you learned it from your primary school teacher, right? Is to write down whatever information from the question in terms of math, right? And then you can how to proceed, right? So the question it gave you is that, right? How likely is if you have drawn a bat A, you get a white is 4/5, because 4 out of 5, right? And you have B that is equal, right? So this is something that we have, and that is the idea that Y is very likely from A, right? If you got a Y, that is very likely from A than B. And both bats are equally likely to be chosen, okay? So that is the information we have, okay? So probably you would first thing to ask is it more likely from A or B? Okay, and you know it's white. So the actual question that given to you is ask you the following, right? Is asking this question: probability given is white is A, or you can calculate this guy. Okay, and do note that they must add up to 1, right? Because either is from A or from B, right? That cannot be from C, right? Because I already described the process. Okay, so then how can we proceed, right? And you notice the question, we have this, right? So basically, I want to do the reverse, right? If you ever pay UNO, right? You just reverse it, right? I remember one famous movie, football clip, I think last week, is someone give him a yellow card, and then the guy pick out the UNO card and reverse. I don't know whether you watch it. That's funny. But this is actually what we're doing. I will do a UNO reverse. Okay. So how can we reverse this guy? And if you remember, it just look back. It just the base rule, right? Reverse. It just reverse it and multiplied by this. Okay. So this is exactly the base rule, okay? And if you look at this, we already have the numerator, right? The numerator is, the first guy is 4/5, the second guy is 1/2, all right? So what is left is the denominator, okay? And the denominator is nothing new, right? The denominator is actually, you can always write in the way that first, we start with the numerator, right? The first part, plus the part that doesn't belong to the denominator is A complement, right? A complement is B, right? And for the first part, right? This part is exactly here. So we're done. This already know, right? We know this guy, we know this guy. So it's done. Everything is known. Nothing new there. So that is actually what you see in the next slide in your handout. Is that okay? Just plug in all the number, then we're done. Okay? Since you are college student, I'm not going to do this. It's already in the slide, right? So you know how that is being calculated, right? So that is let me clear my drawing, right? So it's already here, right? Here what I do is I do the denominator first, right? And I go back to the numerator, right? And then everything is there. Okay. So as you expect, right? If you have a white ball, from A is 8 over 13, B is 5 over 15, 13. So A is more likely than B, right? So it's more likely from A. If the answer would be, maybe I should write that down, right? At the end, it's more likely from A than B. Is that clear? Is there any question? After the break, we will talk about the medical example. Okay. So that's a break. What time is it now? Yeah, that's a break. We will resume at 11:32. So in any case, let's do this as method of the king. As I said, like this, the TA will contact you with consecutively missing the class, and they will try to send care to you. Just try to see if you understand how to do the assignment. To make sure that you're fine. Because I think the faculty require you to have 70% of that. It's now it's no longer focus. I don't think use the class. Make sure watch the video or do it. Otherwise, oh, okay. Sorry. Oh, okay, sorry. Let's see. Yeah, we do that. Let's see. Is it good? That's good. Oh shoot, I can hire her.
你打 OK 嘅嚇咩啊？我都打。
我覺得真係平衡對佢關係。
我唔係緊張，我真係我緊張，我
哋講。
你個 friend
佢要聽啦。
咩話？咩話？你個 friend 又唔係咯？
好大。
唔係，
我哋講翻 exchange。
哦，慢慢繼續講。我最怕你話呢啲好大。
快啲啦！
好大。四個 friend 就要講。
佢一係識㗎嘛 interview 希望佢係會選咩？
有咩問題？有咩做功課唔明？可以有問 B.B.A 嘅。
我哋可以啊！我因為我哋都分咗，我明知佢查嘅。
咪多人睇查。
啲白色四張俾你。
我會分佢。
對。我好想實踐啊！點解我要聽電話？啱啱係講你一定㗎。哦，我哋兩睇電影最多。哇！
佢唔係花咗你。
咁而家帶我去 club。
我寫埋佢寫嘅。
佢啲地方係有對頭嘅。真係
The I睇呢啲好花嘅，即係我同你睇過，所以可能唔係啊，而家份其實佢人
係咯，玩咗好耐。玩咗呢個直發大師僵屍玩過。
唔係啊，我哋其他
我話你做菜泡菜
係咯。
你做個菜俾泡人，泡人外就但係呢個冇泡俾嘅，有啲 friend 專門泡個 friend，專介個 friend 嚟泡。泡嚟泡菜。等間，
咩話？播真係㗎？好風氣啊！
佢咪夾硬寫兩個想點？識你答我。
等，點解你會知嘅？
我誒問香港啲咩私用先冇 OK 啦，有啲成日喺自己嘅即係咩咩咁多，你先有寫出嚟啊嘛。
邊個講咁樣？
有寫出嚟都唔知你識唔識寫。佢專業大家玩錯啦，你都好驚。
你會想你會
你都我哋鬧嗰陣就係睇會同水得上，我哋問得佢有幾個問法嘅。動漫呢個就係我冇係講睇個什麼炸彈嘅，可能冇得辦嘅，但係多啲啦。
咁你都知係嗰啲，
不如我改啦，
嗰啲入唔到。
都 OK，我做得都唔係有人諗嘅，佢聽喺度度諗。
你話咧，人哋咁話你咁樣
幫你哋落個。我巴俾我就
咁咩叫
佢中意你就呢個年化，因為都唔係佢係靚嘅，對你靚誒唔係正靚同靚人嘅對靚啊，呢個中意中意。係，我明白。同埋係，哎呀，我之前全世界問佢呢個問題，即係全世界全部都發生過。咁你嗰唔係，但我之後，唔係啊，但我之後有一日我唔識佢講，我哋咪咁聽佢我話，因為我坐咗咁樣諗。 有啲話係最難，但係做用呢個係呢一個，我哋呢個係確實有一個，所以有啲後面有後面同一齊都係需要佢講係其他都係講嘅，所以呢樣嘢係呢個係
其實都係讀書都得㗎，係咯，俾我。
係啦，即係知道如果你睇實咧，即係呢個就個男仔出嚟嘅，咁然之後咧，而家佢運動花咧，如果佢曬咗運動花，我都開翻出嚟嘅。呢個動方法，即係睇下中國你個數法先嚟同埋我嗰啲動花嘅所有嘅，佢中唔中意嘅動花嘅啦。有啲就係 A 就係中意 A 就係中國話 ，B 就係嘅話，我花嚟咗佢花嚟先嘅話，你如果花嗰個係啦，而家十分之最後最麻煩啦，係啦，我呢個你就攞呢個咁大，因為我有個
So I let me end the end this, okay, and let's see. Okay. So what do you want to say? Will Swarm possibility of evidence decrease the posterior? Oh no. If evidence supporting your prior, then always goes up. Okay, because this is a rational learning. Good. Learning always improve your prior. Okay. If it's more likely. Later you will see the example. It should not go down if evidence favorable to what you learn. No question. Too much revision. Okay, I'm sorry for that. Okay, today is Wednesday. That's good. I think last time we have someone unable to distinguish it's Friday or Wednesday. So this time everyone have slept well. Okay. Oh, is it windy? Okay. So even with this, okay, you can see the example from here. Even with all fact can be edited and reworded differently. So you can see. I hope if they look outside and they update their belief using Bayes' theorem, whether it's going to be the same. One key point, yeah, Bayes' theorem, tree diagram. That's good. So I think I have still have some people who think it's difficult. Yeah, it's very natural. As I told you, if I take the public class, Bayes' theorem is supposed to be the most difficult one. Although if you understand, it's become very natural. But before you understand that, it's very difficult. So let us go to the other example. And hopefully I can convince you this is something that you should learn. And will you always confuse what to use, and while you use it, always go back to this example because this is the most relevant one. Okay? So this example is the following. We have a population and 40% of them is infected. Okay? So this comes from a survey or our prior understanding. This is our prior. Okay, this is our prior. 40% of prior. Okay? And here with some technology, okay? And this technology as a medical test will generate new information which has update a prior, okay? Because the doctor, before you come, right, he will guess what is the number you're having the disease, okay? And the question is, okay, the test is imperfect. And if you ask any student from medical school or any doctor, they will tell you all the tests, no matter what, is always imperfect, okay? It is just depend on the degree, okay? And here we have some experimental data on the effectiveness of the test. Here we have say if you are, that is some data, right? Because you can look at the infected person, right, and give a test to him, and you can see 80% is accurate, right? So 80% of time, your test is going to say give it to the people who actually have disease, right? 80% have that, right? But if you get uninfected people, okay, which is a random people you do, right? Maybe recovered or anyone you know that don't disease, and 40% still are positive. So it's a wrong, right? 60% is correct, but 40% wrong in this aspect, right? So if you learn medical study, they will call false positive and false negative, right? So you have 20% of false negative, right? And 40% of false positive, if you want to use that terminology, but we're not going to do this terminology, just keep this because this is simplest. So the question is, which is very practical, right? And you have prior belief that 40% that patient is infected. After the test, give feedback is positive result. You want to ask how likely that guy have disease, right? So that is a question. Okay. So to put things in the perspective, always, as I said, you always put things into notation that make our life easier because we learn formula makes things easier, right? If you are math oriented. So now the question is like A is our being infected, right? Because A is the prior, right? And B is our information positive result, right? So do note that this means the B complement is negative, right? Because we assume either the test result is negative or positive, right? That's usually what you get as a binary outcome, right? So now we have, of course, you will know A or A complement, right, is not infected, right? Okay. I don't think I need to write that, but this is something that you would in your mind already, right? There's nothing new there because complement, okay? So now to look at the question again, right? The probability A is 40%, right? It's 0.4, right? Because that means you randomly draw a guy, the guy actually has disease 40%, right? That's a prior. And remember, I tell you this is technology tells you, right? Given that you are infected, you have positive results on it that come here. If you are not infected, you get a disease is 0.4. Okay, so that's the information we get, right? And look at the last bullet point. It's just reverse of this guy, right? Reverse, because we want to say if you got positive result, how likely you're infected. Is that clear what we are doing? Is that clear? Right? Do you know that we are coming from this PA to A given B through the process of the test, whether the nature tell whether you get B or B complement. Okay, B and B complement is the information you get. Okay, and we want to ask this question, right? And one natural question you want to ask as well, although you actually we will calculate as well, is what's this guy? Suppose you don't get, sorry, it's A complement different B complement. So if you get a negative report, how likely you are not affected, right? Because that's the thing you want to ask as well, right? I have a negative report, how likely you do it? Because this is what happened when the COVID, right? You get negative report, is it likely that you actually have no COVID? Right. So that's a question. And okay. Now, so how can we do this? Okay. And if you, whatever, right, you see this kind of question, you want to flip something, always base rule, right? Because, or you update, right? Because if basically you get from here to here, right? That's the update with the new information, that's a base rule, right? That's the thing. And how we do that? How we do that? Just remember the formula here, right? We do a reverse cut here, right? And multiply by what conditional on. And so this is the base rule. If you don't remember, just go back to the slide a few ago and end here, right? Because many of you should not have problem why this is true, right? It's there, okay? Or just take it as a surface value. It's true, okay? So how to proceed? It's not complicated, because mechanically with this guy, right? It's here, and we also have this guy, which is here. So the numerator again is done, right? Done. Only left is denominator. Okay, and the denominator is not hard, right? The denominator is simply just write a little bit, right? We will use our total probability rule with the multiplication. You just write, it's very simple. Write the numerator again. That's what we are doing. This numerator, right? This numerator. And we know everything, there's nothing new there. And other part, right? The first part is B with A. The other part is B without A. Let me repeat. The first part is B with A, right? It's B and A, right? The other part is B without A. Right? And the first part we know how to calculate, right? I'm not going to, right? The first part we know how to calculate already because this is exactly from here, okay? And this guy is what? This guy's 0.4. We know how to calculate that, right? And probably what is left is this guy, the very last guy. The very last guy is gone. Probability is not infected, okay? But that is actually prior, right? Because A and A complement must be up to 1 because either you're infected or you're not, right? So it's 0.6. So we know everything. Just plug that in and then we're done. Is that clear? So it's nothing new, but just plug in numbers, understand the question, and that's it. I mean probably you may still worry about why this is true, but mechanically there's nothing but just plug in number there, right? So understanding has several levels, right? The understanding is that understand the formula and plug in, then you understand. But understand deeply, that is something want to do, right? Right. I think in the break I have a joke on this, right? And but anyway, maybe we'll talk about joke later, so forget about the joke. But anyway, is that okay? So the next thing is we want to calculate. This is we'll talk about this as well. So, but before that, I hope it's okay for this one. And actually, this is on the next slide, so the calculation is all there. So I don't think you need to worry, because this is exactly the calculation I written there, but I just do denominator step by step. But exactly you can combine single step there. Is that okay? So what is left is this guy, right? If you have negative, again this diagram, right? Is A and B, A given B will be just the first branch over some of the two branches in the red. Okay, this is exactly the same question. So what will be the next is, this is also you care, right? If the guy has no disease, okay, sorry, you have negative result, what is the likelihood of no disease, right? So you can just apply the base rule here, right? I don't think your problem for this guy, right? Because this is exactly the formula we apply, right? Right? Exactly the formula we apply. If you don't know, just go back and check. You may always confuse with A and B and C, but just keep in mind, okay? In case you can't remember, so you can, if you don't like this is how a high school teacher told me. You can use this. You can have a star and a moon, okay? And this is the moon here, okay? And this is you flip, so star and the moon. Okay, if you don't know, you are confused with the A and B, draw moon and star, and hopefully this will help a little bit. This is how my high school teacher teach when he teach me the math, but I think it's very useful. And also I use this to teach my 5-year-old kids. So I guess that would be good, right? So the only thing you can see, right? Remember, right? The only thing that is a little bit difficult is this guy, the denominator, okay? Because the numerator, we know it, and this one we also know it as well, okay? The only thing is this guy, okay? Again, you can use the same technique, right? But I do a much faster, quick way, because B and B complement are the same. So I don't need to do the complicated total probability rule, just make it faster. Okay, but you can follow what we have done, do the same thing. Okay, so this is a little bit shortcut, but you can do the shortcut because we calculate probability B. But otherwise, you should have done is, you'll be doing is, if you don't calculate this guy, so what you do is you should do this, right? Probability B complement given A and A, right? It's B complement with A and B complement given A complement. Okay, so you'll be doing that. Okay, and all of the probability are known. So these are the two cases. Okay, so as you can see, okay, if originally upon 0.4, okay, you think that guy has disease. If you got a positive result, it becomes 0.7, right? And if you have negative result, it becomes 0.2. Okay, so just tell you something. Is that okay? So now probably this is out of the scope of our class, but I just need to talk one more thing, which I don't put it here. Okay, this is the result. Okay. I didn't mention is what happened if to a second test. Okay, I didn't put it here, but those are QFN, so listen. Okay, because this is the way you do keep updating, because you keep information coming, but our class only update once, okay? But you should know how to update twice, but so actually it's not difficult, right? Remember the formula. Look at the formula. Let's rewrite the base rule again. So this is very technical. So if you don't want to listen, that's fine. Okay. So just rewrite the formula in this way, as I write in the technical part. Okay. Right, this is disease, and this is the update. Sorry. Right. Okay. And you actually jump from this para to this posterior. Okay. And how you jump it, you do one test, right? This is your new thing, right? So if you do and one more round, suppose you do two positive tests, what do you think that guy has disease? So what we're going to do is you will change here, this new value will plug into here. Okay, this guy is technology the same, right? But this guy will be different. So you have to change this guy, and that's it. So the numerator part will be the same, right? But the denominator will be different, right? Because remember, the denominator is what? Denominator is a little bit different, right? Denominator is this guy, right? Have to be very complicated object. But this guy contains this guy, right? So if this change, this also change as well. So basically, if you don't think mathematically, means if you do once, right? And after that, the number of 0.4 will replace the new number, right? So basically what you're going to do is, if you want to do it in principle, it's very simple, right? Because suppose you get a positive result. This gives you like 0.57, right? Like 0.6. So what we're going to do is, you go back to the, right? And the only thing changed in this model, change the scenario, will be just basically change this number, to the one that you just obtained. And we do it again, then done. So it's very simple, because 0.4 is the thing that's given to you. Now you give the one test, if positive, become 0.6, then do all this again. If negative, you do this again. So there's nothing special here. But as I said, this class is not mathy, so I just tell the principle, and you can actually do it. And if you do finance, actually, you keep updating, right? Today, the stock price goes up, you update your belief, and go down with your belief, and you understand what's going on. Okay? So just keep updating, and that's what all the system is doing, right? The AI, right? They try to learn, whether you go to the YouTube or go to TikTok or whatever, right? You like this video, they know how you take this video like they are a comedy, right? Then they keep pushing, go on. This is what they do, the algorithm, right? So the same idea here, right? You keep clicking certain kind of video, they keep going to that kind of video for you, right? So that's the idea. Is that okay? Is there any question? But of course, if you don't understand, multiple updating is fine. I mean, it's not in our syllabus, but just let you know. I mean, the idea is very simple, right? It's nothing new there. Just keep doing. I mean, it's easy to implement in programming, but it's not out of our syllabus. We just ask you to. I think we just ask you to do once. So finally, no more probability. Finally just counting. Okay, and counting. Why we need to talk about this is one. This is in the book, and this is what we will be needing for our random variable. Understand? Okay. So the idea is super simple. The principle of counting. Actually, we learned three things. One is called counting. One is called permutation. One is called combination. Three of them actually in your calculator. Okay. But that is a very simple thing. Okay. Counting is the most simplest. consider the case, the following. You need to complete 2 tasks, okay? And how many possible ways to complete this mission with 2 tasks? Suppose the task 1, you have n1 number of way. Mission task 2, you have n2 of way. How many ways you have? Is n1 times n2. Why? The proof is very simple, because for every way you do task 1, there are n2 ways to do it, right? So that's why you add n to n1 times, which is the meaning of multiplication. Or you can do it by 2 by 2 table, right? n1 by n2 table, and every entry considered as one way to do it, right? So that's multiplication. Okay, so that's why you can generalize. If you have k tasks, each task have n(I) number of way. How many we can do it? Is multiplication multiply together, right? That's the principle of counting. Let's multiply, okay? And I think that is easiest to motivate this from the canteen. This is the example that I got from the canteen, the Franklin canteen. But I don't think they no longer do this. But when this is what I have in my old days, they have simple meal. Okay, I think this is the most expensive 頹飯, the most expensive, cheapest food there. In old days, you can choose rice or noodle. Noodle, I think, is spaghetti. I remember. So there's 3 kinds of meal. You can have pork, beef, or chicken. I think beef is slightly $1 more expensive. At that time, it's like $10. $10, 11, and 12. It's very cheap. When chicken is 10, pork is like the luncheon meat, and the beef is like that. And when that, you choose different sauce. And that's the only good thing about Franklin. You get that you have a red sauce, because the black and white, black is pepper, white is the white sauce standard, right? And the red is, I think, is tomato sauce. I forgot, something like that. It's red. I don't know if it's spicy or not. So the question is, when I was a student, I don't have money, right? So I take that. Then I don't want to make myself terrible, so I don't eat the same meal every day. So the question is, how many possible meals? Okay, very simple. There's a mission with 3 tasks, right? You choose one by one. So the first task is choose the meat, choose dishes is 2, right? And how many meats you can choose? 3. And how many sauces you can choose? 3. Okay, it's 18, right? Consider that you're undergrad, right? You have only 3 days of class usually. Depend on how well you manage to pack your schedule, right? Then you can last for 6 weeks, and usually only 12 weeks for a semester, right? So basically, just repeat yourself once during the whole semester. So pretty good. So this is the way I do. Okay. Probably you guys have much more money in your pocket, so don't have to worry about this. But when I was a student, I do worry about that. So here comes another case where this would be more meaningful to apply the probability, and is the question of what's the probability that sum of the face value is less than 12 when you roll the die twice, right? And to do this, we will use the complement rule, because less than 12, the complement is exactly 12, because at most it's 12, right? And what is how many possible event, right? Because you roll the first die, the 6th outcome, second die also 6. 6 times 6 is 36. And there's only one outcome that's favorable to 12 is 1. So the complement is just 1 over 36. And you find that one subtract from that is what we want to find. So that's why it's what it is, right? Of course, there's nothing new here, but just telling you that the counting is makes things easier. Okay. And the next is permutation. And that's what you do when you do gathering, right? When you're gathering for dinner or lunch, right? And you take pictures, right? Picture it first. Then you take picture, and then you have to take picture together, right? And how many pictures you can take? Okay. If you have n people, right? You can have, suppose you have 4 person A, B, C, D, right? You can A on the first A, B, C, and D, right? And then you want to B, C, D, right? Because the question is like this, right? You also do this when you go to suppose you go to Paris. There's a tower, right? The Eiffel Tower, right? And then you take many pictures. You will take as many as you want, right? Because it's far away from there, from Hong Kong, right? So maybe Mr. A is here, or May. Sorry, should be Miss A is here, right? A is here, right? And the B is here, right? And the girl C is here, right? And maybe both A girl and girl C love the boy, right? Secretly, okay? So they want to change to be next to the boy, right? So how many different photos you can take? Okay? So you can, this is a one way, right? ABC, right? Can be like ACB, right? Can be like CBA, right? Can be like CAB, right? Can also be BAC, right? Can also be BCA, right? So there will be 6 total photo you can take from this one, okay? And how can you derive this 6, right? If you have many people, is there any way to do it quickly? Okay, the answer is very simple. You can think this doing a task, okay? You have to you consider this position, okay? Without putting anyone there, how many ways you can do it? There are 3 persons, so there are 3 ways to do the first one. After which, the second one, how many ways you can do it? 2. The last one is 1, okay? So let me draw a tree diagram to show this is the case. Okay, so it's very simple, right? The first position, you have A, B, and C, right? And the second one, you have, after A, you have B and C, right? After B, you have A and C, right? And after that, you have A and B, right? So this is the second position, right? After that, right? B, then you have only C. C, you don't have B, right? A, you only have C. C, you only have A. This is A, you only have B. And B, you only have C, right? So you can see it's clear multiplication, right? Because the first one, you have 3 different ways. The second task only have 2. The last only have 1 way. So that's why it's 3 times 2 times 1, right? Because that's the way you would do it. Okay. So this is the very standard you can see, right? So in general, if you have n different way to do the first one, n minus 1 and n minus 2, so on and so forth, right? So that's why if you n people, you want to put them on the line or put them in a photo, right? In that case, it will become an n factorial, okay? Which means this exclamation mark is factorial, is stand for you some multiply from n up to the n of the 1, right? So if the n people want to put them there, then it's n factorial. And the thing is, usually you don't use up everything, right? So up to, suppose you only do r of them. So that's why you multiply up to r minus n minus r plus 1. Why plus 1? Because you start from 0, right? You count r times, right? You multiply. This is the first way, second way up to r, but you don't subtract. You subtract 0. You start from 0, so it's minus r plus 1, right? So you can write this as n factorial over n minus r factorial, because the rest is cancelled out. So usually the calculator is called NPR. It appears in your calculator. And if you go to software, the scientific calculator in your iPhone or iPad or whatever, it would be there. Okay. But that is what it means. Okay. So here, let us do the example. You will see why this is important. So again, this is motivated from the thing I eat from Subway, the sandwich store. So I have this when I was working in Singapore for lunch, because Subway is the shop that I don't need to queue. Okay, it's very hot, right? Singapore. So this is a many bread that you can do, but let's simplify with 3 different kind of bread. One Italian grain, and you have to choose 2 ingredients of 6, right? And And the fact that here we have to think about the ingredient, we're very picky. So if we have vegetable on the top of the egg, will be different from egg on vegetable, right? Because you can imagine something can, especially tomato, right? The sauce can go down, right? So some people are very picky. They consider that different, okay? And in that next time, the next slide we talk about when if we consider the order doesn't matter, okay? And if that's the case, how many different ways to do it? First, you choose the bread, so that's why it's 3. Then you choose ingredient, and ingredient we care about order, so we have to choose 6, 2 out of the 6, right? And we cannot choose double tomato or double tuna, okay? Although maybe allowed in some case, but we don't allow that. If that happens, it's 6 times 6, right? But we don't allow that, it becomes 6 times 5, because once you choose, say, tuna, you have to choose finger and tuna. So that's why 6 times 5. So that's a 6p2. Okay. So suppose you are going to choose 3 ingredients, will be 6p3. Okay. So that is very simple. It's 90. Okay. So there's a lot of combination. Now, the very last thing we want to talk about is combination. Okay. Combination will be the case where you would be don't care about the order. All right. It doesn't really matter. You take it out, they take it out. Okay. So the idea of this is just we start from the case where NPR, where the order matters. Okay. But then you double count, you just reverse it. Okay. So why it's important? Let's consider example. Suppose we have 3 persons, A, B, and C. Okay. And we're going to choose 2 of them to represent, to participate in some competition, right? So I mean, then you have C. We have, right? We can have AB, right? And AC, and you have BC, right? Because BA is not counted, right? And AC, CA were the same, or CB the same, right? So if you have 3P2, which is 6, right? But you have to divide for each combination, right? For each, you have 2 ways to do it, right? So that's why you divide it by 2P2, which is actually 2 factorial, right? So just 2. So that's why you only add up with 3. Because for each one you choose, you can read all of them, right? So that's double counting. So that's why you have to divide by R factorial. That is the NCR. Okay? So make an example to do it. So if you don't fully follow, but this is the most important part we'll be using for the next class, is this combination, the idea. So this example we have is how many dishes you can got. Again, this is motivated from the CC canteen, but this is now you can't see it anymore because they change the owner. But this cost you $10 when I was a student. So we have 2 dishes, rice and noodle again, and here you have more. You have a spam and ham and sausage and egg. Okay, and it's black or white, okay, sauce. And for dishes, right, you don't care about whether the sausage on the left or the ham on the right, right? Doesn't really matter because they're not liquid, so that's fine, right? So that should be no problem. So that's why how many possible meals, right? The first task you do is to choose the dish, right? And that's actually what you do, right? You go for the lady serve you rice or noodle, and then you choose one, and then they choose what kind of thing, then it's 4C2, right? Because you choose 2 out of that, and you don't care about order, right? Because you name 2 ingredients there, and at the end you have two sauce you do, right? So it's 4C2. Okay, so 24. So that is the That is the calculation. Of course, I do understand that it's not sometimes not immediately clear. Sometimes this permutation and combination is very difficult. And if you go to the computer science, they study what's called discrete math, and they spend 2 or 3 weeks to understand this kind of calculation, all this how to count stuff. But we are not math class, so this is not considered to be things that we ask. So why we need to do counting is exactly this is the example that why we care. Okay, and exactly we need to understand this one. Okay, we still have 5 minutes, and that's good. So this is the one that you should pay attention, even if you don't understand what has been happening. Okay, and the question is the following: with toes that gone 4 times, what is the probability that exactly we get 2 tails? Okay, of course, you know how many outcomes we have here is 2 times 2 times 2 times 2, because the toes gone 4 times, right? Only 16 outcome. If you are in the high school, you can basically list them all, right? And count how many of them, right? That would be not a problem, okay? And you can do it easily, right? But now we want to talk about how to understand this from the perspective of combination, how to do counting, okay? How we're going to do that is to let me have a whiteboard to illustrate what we're doing. Okay, it's very simple. So what we have is outcomes of 4 toes is either head, tail, 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 or head, head, tail, tail, right? Or tail, head, 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 so on and so forth. There's 16 of them. So how can we convert to the case where we are choosing stuff? Okay, that's very simple. We will call our, if the first, we will consider the following. Consider there are 4 different balls here, right? Because we're always choosing balls, choosing stuff, right? And if the first outcome is tail, okay, we will consider the first ball is being drawn, okay? So in this case, I just consider first ball is being drawn, okay? If this case, I will consider the ball 1, 3, 4 is being drawn, okay? And if I have a tail, if I have tail, head, head, tail, then I consider this is same as 1 and 4 being drawn, okay? Why I do that? Because I want exactly 2 tail, right? So basically means among the 4 balls, I drew 2 balls, right? So basically it's 4C2. Because out of 4, I drew 2, right? Exactly how many of them? Okay? Don't worry, this is the thing that we will do it again when I talk about binomial distribution next class. Okay? This is the thing that why we need to learn it, because this is we're choosing things. Okay? So of course, you can list 16 outcome and count. Actually, there's 4C2, right? But that is the thing we want you to remember, right? This is exactly what I said. I have just said there, right? So 4C2 out of the box is 6. So 6 over 16 is P over A, right? Of course, you can just write that down now, but doing combination is much easier. Okay, so the rest, I don't think I need to talk, especially for the Excel. You just, I'm not going to illustrate. I think it's very simple. Okay, so I will see you on Friday. Have a nice day. Just remember, the assignment has been on. You have 2 weeks to do it. In case of question, ask PA or ask me is fine. Okay. So see you next week. No, see you on Friday.